All right, precalc, chapter 1.1. Let's start the year. Real numbers. We're going to talk about the real numbers today. Well, more than real numbers. There's the non-real numbers or imaginary numbers, which I guess we're not talking about. But you guys should know what real numbers and imaginary numbers are. Yes, does it seem like we're going back all the way to what the heck numbers are? But that's the way math works, right? You kind of recover almost everything you've learned the last 7 years, it seems like, every year. So we figure, hey, a lot of us forget what types of real numbers there are, because they're not all just classified with one set. And so that diagram there of all of the different names kind of highlights what they are. So we got real numbers. Real numbers are the first things we'll talk about. And real numbers are pretty much all the numbers you guys have seen. It can be fractions, it can be whole numbers, or nice numbers, not so nice numbers, positives and negatives, and all of those. So real numbers are pretty much everything you've worked with your whole entire life. Right? 2, -5, pi, e. Those are things you guys should have learned the last couple of years. So that's what it comes down to for there. What's an irrational number? What's a rational number? What's an irrational number? What's a rational number? Can you give me an example of a rational number? Maybe that would be easier. So, okay, an example of a rational number is something like 2. Is -5 a rational number? Sure. What about 1/3? Is that a rational number? Yes. So, rational numbers, guys. I'm not going to write these down. I'm just giving you the examples. You write this down. Rational numbers are anything that can be written, or anything that can be written as a fraction. Anything that can be written as a fraction. 2. 2 can be written as a fraction. What would that fraction be? What would 2 be as a fraction?
2 over 1.
2 over 1. Because anything can be written over 1. Okay? Without having decimals and all those things. So, I think everybody should agree that 2.54 is also rational because it can be written as a fraction. 254 over... What would 2.54... How do you say that? It's not 2.54. How do you actually say that, James? It's 254 of 100 because it's 2 and 54 hundredths, right? So as you kind of say that decimal is what you would put it over. So then if rational numbers are things that can be written as fractions, or, well, there's one more little thing to that, and we'll get to it maybe when we talk about the irrational. Irrational numbers, then, are the ones that cannot be written as fractions. There's actually one other one. So, obviously, pi is an irrational number. You can't write pi as a fraction because the decimal never what? Never stops. So maybe that's another thing. So, what about 1/3? 1/3, I put it in the rational spot. Why would I put it in the rational spot? Why is 1/3 rational? Well, first of all, it can be written as a fraction, you know? But take a calculator out. What is 1 divided by 3? It's 0.3 repeat. So, rational numbers, put this on there, that rational numbers can be decimals, but they have to repeat. Or, just like we have 2.54, it eventually will stop or end. So, going back up to that irrational numbers, pi never stops and never repeats. Someone give me another irrational number that you guys have used. James?
Square root of 2.
Square root of 2. Why? Because square root of 2 is 0.707 la-di-da-di-da. Got it? No, 1.4, sorry. 1.4. 0.707 is the square root of 2 over 2. That's the sine, cosine of 45 degrees, yes? You guys remember those? We'll be dealing with those again. So, okay, irrational numbers, terminal, they don't terminate, their decimals don't terminate, or they don't repeat, can't be written as a fraction. Rational numbers can be written as fractions. They got repeating decimals or terminating decimals. Now, start taking a look at our diagram here, over here. I can use a little arrow. We're talking about real numbers. And our real numbers are pretty much everything you guys can think of. And right now, there are two circles. We got the irrationals, and then we got the rational numbers. And the rational numbers have a bunch of other subsets within it. And the first subset you come across is integers. Integers are the, can't say whole numbers because the whole numbers is a different one inside here. So that's kind of interesting. Integers are the positive and negative nice ones, right? So the positive and negative, kind of the tick marks on a number line, the ones that you like. 2, 3, 2, 3, negative 5, negative 100, right? Those are all integers. Zero would be included in there. I gotta turn the page, so I'll give you guys a second here. So the next one I want to talk about then was what are whole numbers? Whole numbers are a smaller set inside of integers. Whole numbers are the integers, but only what side? The positive side. So it's the positive side of the whole numbers, including 0. So it's 0, 1, 2, 3. When you guys were, I don't know, at what age did you guys start counting? Like, just start counting. I'm trying to think of my own kids. Is that 2? Somewhere around 2? Okay, your parents are like, okay, John, count for us. And then the first number they go, how do they count? 1, 2, 3. I'm pretty sure your parents would go, okay, 0, 1. No, they don't do that. So our natural numbers are the naturally way you learned your numbers, which was starting at 1, 2, 3, on. I'm going to go back to that diagram we had. But natural numbers starts at 1, 2, 3, 4, 5, goes on. Whole numbers brings in 0. Integers goes backwards. The nice numbers going into the negative direction as well. And I'm going back. And then we go to rational numbers, which can include the decimals and fractions, which are all parts of real numbers. And we also have something called irrational numbers. Those are basically your numbers. You're going to have a part in your homework that says, classify this number. Is it a whole number? If it's a whole number, that means it also must be an integer, which means it also is a rational number, which is a real number. What would be a non-real number? I don't have that up here. We should probably talk about that. We're in pre-calc. What's not real? Yeah. Is it, no.
Izzy.
Izzy.
Yeah. I.
I. What is I?
Square root of -1.
Square root of -1. So the square root of -1 becomes I. You poke an eye out if you had Havlicek before. And so that is true. So square roots. The definition of a square root is a little bit trickier than just saying what is a square root. Like the square root of 36 is 6. It's pretty easy. We all have been doing that for so long. So the definition that the book used is it's one factor, or one of two. One of two equal factors of a number. So, why is the square root of 25 5? Because 25 is made up of two equal factors of 5 and 5. Now, when I asked you square root of 100, square root of 121, 144, all of those things, and you guys just spit one answer out, you guys are giving me examples of the principal square root. Because we should know that if I said x squared equals 25, what are the values of x? It's been a while. When I go to solve an equation and having to use square root, I have to have what? Plus and minus, or negative and plus. So we got a 5 and a negative 5. The principal square root is the positive partner, or the positive square root. So we have the positive square root. And a perfect square. Give me an example of a perfect square. 4 is a perfect square. What else? 16. Why? Because they all have a perfect square. Well, there are perfect squares. It's kind of, you can't use the definition there, right? So they're perfect squares because the square roots are rational. It's kind of weird how they say that. So they have rational square roots. So we can talk about the different properties of real numbers. So we have the commutative properties. Basically, the commutative property says that A plus B is the same thing as B plus A. The commutative property of addition. We also have A times B is equal to B times A. You can take the order when adding or multiplying. It's the same thing. 2 times 3 is 3 times 2. We all should agree with that by now, right? And that's what we're highlighting there. We also have the associative property. The associative property when adding or multiplying says that you can add 3 different numbers and you can add different pieces at different times. So you can add the first 2 together, find that result, or that sum, and then add the third one. Or you can add the last 2 and then add the first one. These are things that we've done many, many times in our life. And actually, some of these make our life easier in math. Think of times when you try to add a large group of numbers. You either try to make 10s or 100s, right? You're always trying to get to that magic number that things start to cancel out or go away. You start going through your list a little bit faster. Same thing with multiplying 3 different numbers together. And then, of course, we have the distributive property. The distributive property, if you have a variable or a number out front, you can distribute it in. Notice that on this one, they put the A, which was being distributed in front. But on the second example down below, A was coming from the back, and ends up being, oh, they still put it in the front. A lot of times in a lot of books, they actually leave that order, wherever it comes from the front or from the back, they'll leave it in that position. We're talking about real numbers, it doesn't matter. How many people did the matrices stuff? Did multiplying matrices? You remember when you multiply matrices, A times B is not the same as B times A? So that's where kind of, you may want to keep your order the same. Next up, we're talking about fractions. Now we're starting to talk about different things here. We got the multiplicative identity. A times 1 is A, or 1 times A is A, right? Using the commutative property there. Basically, anything times 1 is itself. That's the identity for multiplication. We also have the inverse identity. It says every non-zero value of A, right, has an inverse of 1 over A. Basically, reciprocal. Such that when you multiply A times its reciprocal, what happens? What do you get? You get 1. Because the A's will cancel. They'll divide out. A over B refers to the blank of A and B. Yeah, I kind of left that. Got to fill in the blank. The fraction itself of A divided by B, we sometimes can use what phrase? The blank of A and B. Not reciprocal because we don't have another one to look at. Starts with the Q. Quotient. So we have the quotient. The quotient of A and B, basically, aka we call that a fraction. I think I already used that word. We just call them fractions. But you guys better get used to the idea that if you have the quotient of two things, the first thing in that sentence is on top, and the other one's on the bottom. Wait a minute, the next line below kind of says, hey, wait a minute, the top is called the what of a fraction? Yeah. Numerator. And the bottom? Denominator. So if we're going to talk about fractions, well, I guess we might as well talk about their properties as well. This one just mostly tells us how to use those fractions appropriately. Like when you are multiplying fractions, what do you do? Multiply just across, right? So A times C is in the numerator, B times D is in the denominator. Basically, if you don't want to copy all that down because you don't have them printed out, make sure you say, when multiplying fractions, you multiply across. A lot of people want to take those and multiply their corners. Now, let's consider cross multiplication. When do we ever use cross multiplication? When there is a what between the fractions? What's that? Yes, equal sign. I thought you said cosine there first. So, when you're multiplying, multiply across. The second group is dividing. When you divide by a fraction, what do? Yes, multiply by the reciprocal. The reciprocal of which one? The second one, or the one that is after the division sign. So notice in this example, C over D becomes D over C, and we're multiplying here. And obviously we got an example there that you guys can see that does that. 3 and 4 are adding or subtracting. Doesn't matter. You can add a negative if you wanted. But in 3, we're adding fractions. When you add fractions with like terms, what can you do? Like denominators. That's the terms like denominators. So what can I do here? What do I do with the numerators then?
You just add them and keep the denominator the same.
Add the numerators, keep the denominator. When you go below to the problem on below it, the denominators are not the same. So therefore you need to do what? You need to common denominator. Find the common denominator. We can find any common denominator. I think that'll work. But what's the most efficient one? Yes, least common denominator, the LCD. The LCD, and that is the least common denominator. Okay, so least common denominator. What are some ways to find the least common denominator? So the problem they have is a 5 and a 7. If you look in the bottom here, how did they get 35? What's one way to find a common denominator? First of all, Claire. Yeah, just multiply both denominators. Now sometimes if we're talking about a 12 and a 10, that's 120. That's a big number, right? And remember, what you do to a denominator, you have to do to a numerator. And we're going to do that in the next example. So you probably don't want to necessarily use just multiplying them together. What is then a different way to figure out what they both go into? Because I say, let's use the idea of 12 and 10. Those two numbers there at the bottom. We know 120 would be a common denominator. What's the least common denominator? Does anybody know? 60. It's 60. How did you figure that out? You just knew it. But what's a practical way of figuring that out? There's a couple different ways. You guys can count by 12s. Can you write, 12, 24? Well, you know 10. 10 has to end in a 0. So 12, 24, 36, 48, 60, right? That's one way to do that. Actually start to multiply it out or keep adding multiples of those numbers until you get a common number. That's one way. The other way, guys, is to factor each one of those. What are the factor pairs, or the factors, actually, of 12? 2 and 6, but 6 can be broken down to 2 and 3, and 10 is 2 and 5. So they have 1, 2 in common, so I can grab one of them. Actually, I should say, you have to grab the most of every kind. So there are 2 2's on the left one. There's only 1 2 on the right. So you need 2 2's. There's a 3, and then there's a 5. What happens when you multiply all those together? You get 60. So you kind of have to grab the most factor pairs of each kind, and then you can get one. So there's a couple different ways that you can find the LCD. So our first example that will test some people's typing skills. Using the LCD to add these fractions, please add them together. And this is where 36 and 120, both semi-large fraction or denominators. I'm guessing most of us would not want to take 36 and times it by 120 to find the denominator, or the LCD. So I'm pretty sure that's not the LCD. And I'm pretty sure most of us don't want to keep adding 36 either. So, again, we could go to our other option there and say, what are the factor pair, or the factor tree, I guess, the factors that make up 36? "36 is 6 and 6, 2 and 3, 2 and 3, yes? Yes. So that means it's 2, 2, 3, 3. Okay, so we know we have 2 2's. Some of us have 2 2's. And 2 3's. And the other one was 120. What are some pairs of 20? 2 and 60, 2 and 30, 2 and 15 if you want. I just like to keep going with my 2's. Can't do 2 anymore. I can do a 3 and 5. So we know we have 2, 2, 2, 3, and 5. So, what is the number going to be? How many 2's do I need? You need 3 of them because he has 2, This one has 3, so you need all 3 of them. Bless you. How many 3s? 2 of them. And a 5. Oops. Multiply all those back together. 2 times 2 times 2 times 3. 24 times 3. 72 times 5. 360? You guys are quicker than I am on that. So 360. Well, that's not too bad then. Now, if I wanted to use that, how do I use that? So fine, we found the LCD. Now what do? What's the goal? Make the denominators 360. How do I make 36 a 360? Multiply it by 10. And if I multiply the denominator by 10, I have to multiply the numerator by 10. Going over to 120, what do I have to multiply that one by? 3. And so, 10 times 5, 50 over 360 plus 21 over 360. And you end up with an answer of 71 over 360. Am I done? Well, if it were reduced, then it'd be fine, right? So, 71, I don't think if there's too many factors of 71. So, there we go. So, day 1, your homework is page 12, 1 through 16. The first group of homework is just identifying what property, commutative, associative, those types of things. Next one is use the properties of real numbers to write the expression without parentheses. Not too bad. And then the last one is adding, subtracting fractions. Make sure you use your order of operations. Have a great day.